The speed of light isn't the limit anymore. Forget everything you know about speed limits. Faster than light travel just went from fantasy to physics. Scientists cracked something that shouldn't exist. Something extraordinary is unfolding in the world of physics. If you're curious where this goes, subscribe to the channel. Every video we create is designed to bring you the latest discoveries. Now let's get started. Imagine you're standing on a moving walkway at an airport. You're not walking, but you're still moving forward because the floor beneath you is carrying you along. That's basically what a warp drive does, except instead of a conveyor belt, you're riding a wave of space-time itself. And because you're not technically moving through space, you're not breaking any laws of physics. Einstein's speed limit, the speed of light, only applies to objects moving through space. It doesn't apply to space itself, but there was always a catch. A massive, seemingly impossible catch. To create this warp bubble, Alcubierre's original calculation suggested you'd need an enormous amount of exotic matter. And by enormous, I mean more negative energy than seems to exist in the entire observable universe. Negative energy is strange stuff. It's not like the energy you get from burning gasoline or splitting atoms. It's energy with a negative value, something that pushes instead of pulls, that repels gravity instead of attracting it. We've seen hints of it in quantum physics in phenomena like the Casimir effect, where two metal plates placed incredibly close together in a vacuum experience a tiny, attractive force. That force comes from negative energy fluctuations in the quantum vacuum, but harnessing enough of it to power a warp drive, that seemed utterly impossible. Until now. The breakthrough I'm telling you about changes the game. This new warp drive design, published by researchers studying what's called irrotational warp fields, dramatically cuts down the negative energy requirement. How did they do it? By removing something called vorticity from the space-time flow. In simpler terms, they smoothed out the rotation and turbulence in the way space-time gets warped. Imagine trying to create a whirlpool in water versus creating a smooth, gliding current. The whirlpool takes more energy and creates more chaos. The smooth current is efficient and stable. That's what these scientists did with space-time itself. And here's where it gets even more mind-blowing. They didn't just reduce the energy requirement. They also made the warp bubble more stable. Earlier warp drive models had a problem. The stress and energy densities, the forces acting on the fabric of space-time, were so extreme and chaotic that physicists worried the whole thing would collapse or tear itself apart. This new design keeps everything under control. It's what physicists call Hawking-Ellis Type 1, which is a fancy way of saying the energy behaves in a well-defined, predictable manner. There's still negative energy involved, but it's manageable, it's contained, and that's huge. Speaking of extreme environments and the bizarre nature of space, if you want to understand just how hostile the universe really is, check out my video called The Terrifying Truth about how cold space really is, on the card above. It'll give you a whole new perspective on what it takes to survive out there, and why breakthroughs like warp drives aren't just about speed. They're about making the cosmos accessible to fragile beings like us. Now let's zoom out for a second and think about what this all means. We live in a universe that's almost incomprehensibly vast. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. That means if you traveled at the speed of light, which nothing with mass can do, it would still take you over 4 years to get there. The Voyager 1 spacecraft, humanity's most distant ambassador, has been traveling for nearly 50 years and has barely left our solar system. It would take Voyager more than 70,000 years to reach Proxima Centauri. 70,000 years. That's longer than all of recorded human history. But with a warp drive, you're not constrained by that speed limit. Theoretically, you could reach Proxima Centauri in weeks, days, maybe even hours, depending on how fast you can warp space-time. You could explore exoplanets orbiting distant suns. You could visit star systems thousands of light-years away. You could venture to the heart of our galaxy, to the supermassive black hole lurking at its center and return home before your loved ones have aged more than a few years. This is the promise of faster-than-light travel. Not just speed, but the conquest of cosmic distance itself. But let's be clear about something important. We haven't built a warp drive yet. What we have is a mathematical model that works on paper, a set of equations that show it might be possible. And that's still incredibly significant because, for decades, even the equations seemed impossible. The energy requirements were so absurd that most physicists dismissed the whole idea. Now we have equations that look achievable, not easy, not something we'll build tomorrow, but achievable. And in science, that's often how breakthroughs begin. First comes the mathematics, then comes the engineering. There's another fascinating development happening in parallel. In 2021, a team led by physicist Alexei Bobrik and entrepreneur Gianni Martira published research suggesting that certain types of warp bubbles might not need negative energy at all, at least not for subliminal travel, meaning speeds slower than light. Their work proposed a new classification system for warp drive spacetimes, showing that some configurations could theoretically use positive energy, normal energy, the kind we can actually generate. Now, these wouldn't get you faster than light, but they could still propel a spacecraft at significant fractions of light speed without requiring conventional rockets. And that alone would revolutionize space exploration. Think about what that means. Even if we can't break the light barrier right away, we might still be able to cruise through the solar system and beyond at velocities that make interstellar travel feasible within a human lifetime. Mars in days instead of months. The outer planets in weeks instead of years. The nearest stars in decades instead of millennia. Each step forward opens new possibilities. And then there's Harold White, the former NASA physicist who has been chasing the warp drive dream for years. White made headlines back in 2021 when his team at the Limitless Space Institute discovered something unexpected. They were studying tiny structures called Casimir cavities, microscopic spaces where quantum effects create measurable forces. While analyzing the energy distribution in these cavities, they noticed something peculiar. The pattern of negative energy density they measured looked remarkably similar to what you'd need for an Alcubierre warp drive. It was accidental, unintentional, but there it was, a tiny warp bubble signature potentially forming in a laboratory setting. White and his colleagues didn't claim they'd created a warp drive. They were careful about that. But they showed that the energy structures required for warp drives might naturally emerge under certain quantum conditions. And that's tantalizing, because if nature can create these conditions on a microscopic scale, maybe we can scale them up. Maybe we can engineer them deliberately. More recently, in December of 2025, White published another groundbreaking paper in the journal Classical and Quantum Gravity. This time, he introduced a segmented warp drive design. Instead of a single, smooth ring of warped spacetime surrounding the spacecraft, imagine multiple cylindrical structures like nacelles arranged around the ship. Sound familiar? It should. That's basically the design of the USS Enterprise from Star Trek. 2 warped nacelles flanking the main hull. It turns out the science fiction writers might have accidentally stumbled onto something physically plausible. White's segmented design has some major advantages. It distributes the energy load more evenly. It reduces the peak stress on any single point in spacetime. And it makes the whole system more stable. Think of it like distributing weight across multiple support beams instead of balancing everything on one central pillar. The engineering becomes more manageable. The physics becomes more forgiving, but here's where we need to talk about the elephant in the room. Energy. Even with these new, more efficient designs, we're still talking about energy requirements that dwarf anything humanity can currently produce. The improved warp drive models might need 38 times less exotic energy than Alcubierre's original concept, but that's still an enormous amount. We're talking about energy levels comparable to the total output of a star. Not for a second, but sustained over time. And negative energy remains a problem. We know it exists. We've detected it in quantum experiments, but we've never created it in macroscopic quantities. We've never harnessed it, stored it, or controlled it in any meaningful way. The Casimir effect produces negative energy, sure, but only in amounts so tiny you'd need a microscope to measure them. Scaling that up to power a spacecraft is like comparing a birthday candle to the sun. So why am I telling you all this? Why share these breakthroughs if we're still so far from actually building a warp drive? Because this is how science works. This is how humanity has always pushed forward. We start with mathematics that seems impossible. Then we refine the mathematics until it seems merely improbable. Then we start experimenting. We iterate, we fail, we learn, and eventually we succeed. Consider flight. In the late 1800s, most scientists believed heavier than air flight was impossible. They had sound mathematical reasons for that belief. The energy requirements seemed too high, the engineering challenges too great. And yet, on December 17, 1903, two bicycle mechanics from Ohio proved everyone wrong. Wilbur and Orville Wright flew. They didn't fly far and they didn't fly high, but they flew. And within 66 years of that first flight, humans walked on the moon. Or think about nuclear energy. In 1933, the renowned physicist Ernest Rutherford called the idea of extracting useful energy from atoms moonshine, just one day before Leo Szilard conceived the nuclear chain reaction. Within 12 years, humanity had built nuclear reactors and, tragically, nuclear weapons. The impossible became reality faster than anyone imagined. The same pattern has played out again and again throughout history. Rockets to space, computers in every pocket, instant global communication, gene editing, artificial intelligence. Each of these technologies began as mathematical speculation. Each faced seemingly insurmountable obstacles, and each eventually became part of our everyday reality. That's the context you need to understand these warp drive breakthroughs. We're in the mathematical speculation phase, the equations are getting better. The energy requirements are becoming less absurd. The physics is moving from absolutely impossible to extraordinarily difficult. And that's progress. Real, meaningful progress. There's something else happening that makes this moment particularly exciting. Our understanding of space-time itself is evolving. For over a century, Einstein's general relativity has been our best description of gravity and the structure of the universe. But we know it's incomplete. It doesn't play nicely with quantum mechanics. At the smallest scales and the highest energies, general relativity breaks down. We need a theory of quantum gravity, a framework that unifies the physics of the very large with the physics of the very small. Several candidates for this unified theory exist. String theory, loop quantum gravity, causal set theory. Each approaches the problem differently, but they all suggest that space-time might be more flexible, more malleable than we previously imagined. And if space-time is more flexible, then manipulating it for purposes like warp drives might be easier than Einstein's equations alone would suggest. We might discover shortcuts, loopholes, new physics that makes the impossible merely difficult. And here's something that should make you sit up and pay attention. In May of 2026, just weeks ago, physicists at the University of New Brunswick published research testing something called the ER equals EPR conjecture. This is a mind-bending idea that connects quantum entanglement, where two particles remain mysteriously linked across any distance, with wormholes, those hypothetical tunnels, through space-time. The conjecture suggests that every pair of entangled particles might be connected by a microscopic wormhole. A tiny Einstein-Rosen bridge threading through the fabric of reality itself. Now, why does this matter for warp drives? Because if quantum entanglement and wormholes are two sides of the same coin, then the universe already has mechanisms for connecting distant points in space-time. Nature is already doing something that looks an awful lot like faster-than-light communication, at least in terms of correlating quantum states. We don't fully understand how it works yet, but the fact that it works at all suggests that space-time has properties we're only beginning to uncover. Properties that might make technologies like warp drives more feasible than we think. The New Brunswick researchers didn't prove the ER equals EPR conjecture, but they constrained it. They showed that if it's true, it would have subtle effects on atoms, effects we haven't yet observed. That doesn't disprove the idea. It just means nature is more subtle than we thought. And subtlety in physics often means there's something deeper waiting to be discovered. Another layer of reality we haven't peeled back yet. Let me paint you a picture of what the universe looks like from the perspective of modern physics. Space-time isn't a rigid stage where events happen. It's a dynamic, flexible fabric that bends and warps in response to matter and energy. Every planet, every star, every galaxy creates a dent in this fabric. That's what gravity is. Not a force pulling things together, but the geometry of space-time itself, curved by the presence of mass. Now, light travels through this curved space-time at a fixed speed, roughly 300,000 kilometers per second. Nothing with mass can match that speed, let alone exceed it, because as you approach light speed, strange things happen. Time slows down for you relative to the outside world. Your mass effectively increases, requiring ever more energy to accelerate further. It's an asymptotic barrier. You can get closer and closer to light speed, but you can never quite reach it. But here's the beautiful loophole. That speed limit only applies to objects moving through space-time. Space-time itself has no such restriction. The fabric of the universe can expand, contract, and move however it wants. In fact, we know it does. The universe itself is expanding, and distant galaxies are receding from us faster than light. Not because they're moving through space that quickly, but because the space between us and them is stretching. The galaxies are just going along for the ride. A warp drive exploits this exact principle. Instead of pushing a spacecraft through space at impossible speeds, you manipulate the space around it. You contract space-time in front and expand it behind, creating a wave that carries the ship along. From the ship's perspective, it's sitting still inside a bubble of normal space-time. But from an outside perspective, that bubble is moving, potentially faster than light. It's elegant, it's ingenious, and it doesn't violate relativity because the ship itself never exceeds light speed relative to its local space-time. The local environment moves instead. Einstein's equations not only allow this, they practically invite it. The mathematics works. The question has always been whether the engineering can work too. And that brings us back to energy, specifically negative energy. To warp space-time the way we need for a warp drive, you have to violate something called the null energy condition. This is a rule that says energy density, as measured by any observer, should never be negative. It's not a fundamental law like conservation of energy, but more of a consistency condition that keeps space-time from doing weird, pathological things. Most classical forms of matter and energy obey it, but quantum fields don't always. The Casimir effect is the most famous example. Place two uncharged metal plates extremely close together in a vacuum, and they'll attract each other. Why? Because the quantum vacuum isn't truly empty. It's filled with virtual particles, fleeting fluctuations of energy that pop in and out of existence. Between the plates, only certain wavelengths of these fluctuations can fit. Outside the plates, all wavelengths exist. This creates a pressure difference, a region of negative energy density between the plates that pushes them together. The effect is real, it's been measured countless times, but the amount of negative energy involved is infinitesimal. To generate enough for a warp drive, you'd need Casimir plates with the surface area of a planet separated by distances smaller than an atom. Clearly not practical, but it proves the principle. Negative energy exists. Nature uses it. We just need to figure out how to produce it in useful quantities. Harold White's Casimir cavity experiments hint at a possible path forward. By creating complex three-dimensional structures on the microscale, he and his team found configurations that produce energy patterns remarkably similar to what you'd need for a warp bubble. These aren't full-scale warp drives, not even close, but they're proof-of-concept demonstrations. They show that with the right geometry and the right materials, you can coax quantum fields into doing what you need. Other researchers are exploring different avenues. Some are investigating exotic materials that might have negative mass or negative energy density under certain conditions. Others are looking at rotating black holes, which create regions of space-time with strange properties that might be exploitable. Still others are studying the cosmic strings, hypothetical defects in space-time left over from the early universe, which could theoretically be used to warp space in useful ways. None of these approaches have yielded a working warp drive yet. But each one adds another piece to the puzzle. Each one expands our understanding of what's possible, and each one brings us incrementally closer to the day when faster-than-light travel might transition from science fiction to science fact. Let's talk about what a real warp drive mission might look like, assuming we solve the energy problem. Imagine a spacecraft maybe the size of a large house, sitting inside a football-shaped bubble of warped space-time. The crew inside experiences normal gravity, normal time, normal physics. They could walk around, eat dinner, watch movies, completely unaware that they're moving faster than light relative to the outside universe. Outside the bubble, things look very different. Space ahead of the ship compresses, bunching up like a wrinkled carpet. Space behind stretches out, expanding like taffy being pulled. The bubble itself surfs along this wave of distorted geometry, carrying the ship with it. To an outside observer, the ship would appear as a blur, a distortion in the starlight, moving at velocities that defy common sense. The journey to Proxima Centauri, our nearest stellar neighbor, might take weeks instead of thousands of years. The trip to the center of our galaxy, 26,000 light-years away, might take months instead of eons. You could visit the Andromeda Galaxy, 2.5 million light-years distant, and return within a human lifetime. The universe would suddenly become accessible in a way it has never been before. But there are complications, serious ones. For starters, steering a warp bubble might be impossible. Once you create the bubble and set it in motion, you're trapped inside. You can't send signals out because any light or radio waves you emit get caught in the warped space-time around you. You can't see where you're going because the light from stars ahead gets severely blue-shifted and distorted. You're essentially flying blind inside a cosmic surfboard, hoping you programmed the right destination before you launched. Then there's the problem of what happens when you stop. As you travel through space at faster-than-light speeds, your warp bubble sweeps up particles, radiation, and stray atoms floating in the interstellar medium. These accumulate at the leading edge of the bubble, building up energy. When you finally collapse the bubble and return to normal space-time, all that accumulated energy gets released in a catastrophic burst. We're talking about radiation levels that could sterilize planets, destroy space stations, or fry anything in front of your ship. A paper published by physicist William Clark in 2012 calculated that stopping a warp drive near a planet could release enough energy to destroy continents. It's like traveling the galaxy with a doomsday weapon strapped to your front bumper. You'd need incredibly precise control and probably some way to shunt that energy safely away before arriving at your destination. Otherwise, every warp drive journey becomes a potential existential threat to wherever you're going. There's also the causality problem. Faster-than-light travel opens the door to time travel paradoxes. If you can move faster than light in one reference frame, then from another reference frame, you're moving backwards in time. This doesn't necessarily mean you could go back and prevent your own birth, but it does create thorny problems for the logical consistency of space-time. Some physicists argue that the universe has built-in mechanisms to prevent these paradoxes, something called chronology protection. Others aren't so sure. These aren't trivial concerns. They're fundamental challenges that need solutions before warp drives become practical, but they're also the kind of problems that make physics exciting. They push us to understand space-time more deeply. They force us to confront the weird implications of Einstein's theories, and they remind us that the universe is far stranger and more wonderful than our everyday experience suggests. Now let's talk about what all this means for humanity's future. If we do eventually develop warp drive technology, it wouldn't just change space exploration, it would transform civilization itself. The barriers that currently confine us to one tiny blue planet, orbiting one ordinary star in one corner of one galaxy, would fall away. We'd become a truly spacefaring species capable of spreading across the cosmos. Think about the possibilities. Entire cities built in orbit around distant stars. Research stations established in exotic environments near black holes or neutron stars where the laws of physics play out in their most extreme forms. Mining operations extracting resources from asteroids and planets across hundreds of star systems. Scientific outposts studying alien worlds, searching for life in all its possible forms. And maybe, just maybe, we'd encounter someone else out there. Other civilizations, other beings who look up at their night sky and wonder if they're alone. The universe contains hundreds of billions of galaxies, each with hundreds of billions of stars. The odds that we're the only intelligent life seem vanishingly small, but the distances are so vast that without faster-than-light travel, we might never meet our cosmic neighbors. A warp drive changes that equation entirely. Of course, this raises profound questions. How would contact with alien civilizations affect human culture, human religion, human identity? What would we learn from beings who evolved under completely different conditions, who might think in ways we can't even imagine? And what responsibilities would we have as we venture into the galaxy? Would we be explorers or invaders? Ambassadors or conquerors? These are questions our descendants might have to grapple with sooner than we think. But I'm getting ahead of myself. Before any of that happens, we need to solve the energy problem. And that's where things get really interesting, because the search for new energy sources has always driven technological revolutions. The discovery of fire, the invention of the steam engine, the harnessing of electricity, the splitting of the atom, each breakthrough unlocked new capabilities and reshaped civilization. Developing the technology to power a warp drive would require energy generation and manipulation far beyond anything we currently possess. We're talking about energies comparable to stars, controlled with precision down to the quantum level. That's not just an engineering challenge, it's a fundamental leap in our relationship with the physical world. And historically, when we make leaps like that, the benefits ripple out in unexpected ways. The Apollo program, which put humans on the moon, cost about $25 billion in 1960s money, equivalent to over $150 billion today. It was expensive, it was risky. Many people questioned whether it was worth it. But the technologies developed for Apollo, everything from miniaturized electronics to advanced materials to computer guidance systems, ended up transforming everyday life. The economic returns far exceeded the initial investment. A serious warp drive research program would likely follow a similar pattern. The technologies developed along the way, new materials, new energy systems, new methods of manipulating quantum fields, would find applications far beyond space travel: medical devices, communication systems, manufacturing techniques, energy production. The pursuit of one audacious goal often yields benefits in 1,000 unexpected directions. And there's something else worth considering: the sheer inspiration value. Human beings need big dreams. We need challenges that pull us forward, that unite us in common purpose, that remind us what we're capable of when we work together. The space race of the 1960s inspired an entire generation to pursue careers in science and engineering. It showed people around the world what humanity could achieve when we set our sights on seemingly impossible goals. A serious effort to develop warp drive technology could do the same thing today. It could capture imaginations, it could inspire young people to study physics, mathematics, and engineering. It could give us a shared vision of the future that transcends national boundaries, political divisions, and cultural differences. Because ultimately, the exploration of space isn't about any one country or any one group. It's a human endeavor, a species-level adventure. And here's something beautiful to consider. We are, quite literally, made of stardust. Every atom in your body, except for hydrogen, was forged in the heart of a star. The carbon in your cells, the calcium in your bones, the iron in your blood, all of it came from stars that lived, burned, and died billions of years ago. Those stars exploded as supernovae, scattering their enriched material across space. That material eventually coalesced into new stars, new planets, and eventually us. You are the universe experiencing itself. You are billions of years of cosmic evolution, organized into a form capable of looking back and wondering where it all came from. And now that same universe is trying to figure out how to explore itself more efficiently, how to traverse its own vast distances, how to connect the scattered islands of matter and energy that float in the cosmic ocean. There's a poetry to that, a symmetry. The warp drive research happening right now is part of that grand story. Scientists working in laboratories, staring at equations on whiteboards, running simulations on supercomputers, they're not just solving technical problems. They're participating in the universe's ongoing quest to understand itself. They're pushing against the boundaries of what's possible, and every small success, every refined equation, every reduced energy requirement brings us one step closer to becoming the spacefaring civilization we've always imagined. Let me share with you some of the other fascinating work happening in this field right now. In 2026, researchers using the KM3-Net neutrino detector tested whether neutrinos, those ghostly particles that barely interact with matter, might travel faster than light. The results? Neutrinos obey the speed limit. They don't exceed light speed, at least not within the precision of our measurements. This might sound disappointing, but it's actually valuable information. It tells us that if there are loopholes in relativity, they're subtle. They require exotic conditions or specialized mechanisms. You can't just throw more energy at a particle and push it past light speed. But here's where it gets interesting. That same research confirmed that the fabric of space-time itself is incredibly robust. The fact that neutrinos, which have traveled across billions of light-years of space, still obey Einstein's rules so precisely tells us that space-time isn't full of shortcuts or cheats. If warp drives are possible, they'll require deliberate manipulation of space-time's geometry, not just exploitation of some natural loophole. That's a higher bar, but it's also more promising in a way. It means that when we do figure it out, we'll have real control over the process. There's also groundbreaking work on something called optical phase singularities. In April of 2026, researchers at Technion in Israel measured dark points within light waves, vortices where the amplitude drops to zero, and found that these points can move faster than the light waves themselves. Now, before you get too excited, this isn't information traveling faster than light. It's a pattern, a structure within the light field, moving at superluminal speeds. But it demonstrates something important. The universe is full of subtle effects where things that seem impossible actually happen under the right conditions. These dark points in light waves confirm predictions made 50 years ago by physicists John Nye and Michael Berry. For half a century, we knew theoretically that this should be possible, but we couldn't measure it. Now we can. And that pattern, theoretical prediction, followed decades later by experimental confirmation, is common in physics. Einstein predicted gravitational waves in 1916. We didn't detect them until 2015, nearly a century later. Sometimes the mathematics leads and the technology catches up generations later. That's actually encouraging. For warp drive research, we have the mathematics now. We have models that work on paper, with energy requirements that are dropping as the models improve. Maybe in 20 years or 50 years or 100 years, we'll have the technology to test them, and maybe those tests will reveal new physics, unexpected shortcuts, ways to make it even easier than our current models suggest. There's another dimension to this story that we haven't fully explored yet, the philosophical dimension. What does it mean for humanity if we can travel faster than light? How does it change our place in the universe? For all of human history, we've been bound to Earth. Even our ventures into space, landing on the moon, sending probes to the outer planets, barely count as leaving home. We're still in our own cosmic backyard, huddled close to our parent star. Faster than light travel would fundamentally change that relationship. We'd no longer be prisoners of distance. We'd no longer be confined to one star system, hoping against hope that we can somehow squeeze out an existence among the handful of planets orbiting our sun. We could choose our destinations. We could seek out the most interesting, the most beautiful, the most habitable worlds in the galaxy. We could become citizens of the cosmos in a real, meaningful way. But with that freedom comes responsibility. The galaxy isn't empty. It's full of worlds, some barren, some teeming with life, some perhaps hosting civilizations of their own. How we conduct ourselves as we venture outward will define what kind of species we are. Will we approach exploration with humility and respect? Will we recognize that every world, every ecosystem, every potential civilization has intrinsic value? Or will we repeat the mistakes of our own history, treating the cosmos as territory to be conquered and exploited? These aren't abstract questions, they're practical considerations that future generations will face. And the choices we make now, the values we instill in our culture, the ethics we build into our institutions, will shape how those future generations approach these challenges. The dream of faster-than-light travel isn't just about technology, it's about who we want to be as a species. Let me bring this back to the science for a moment, because there's another exciting development I want to share with you. In May of 2026, researchers studying the ER equals EPR conjecture, the idea linking quantum entanglement with wormholes, published results that constrain how this connection might work. They showed that if entangled particles are connected by microscopic wormholes, those wormholes would have to be incredibly subtle. They can't be obvious tunnels through space-time. They have to be something more delicate, more quantum, something that operates below the threshold of classical observation. This matters because it suggests that space-time at the quantum level is far richer and more complex than we previously imagined. There might be an entire hidden architecture connecting distant points in space, threading through dimensions we can't directly perceive. And if that architecture exists, then maybe, just maybe, we can learn to tap into it. Maybe warp drives aren't just about brute force manipulation of space-time geometry. Maybe they're about finding and exploiting structures that nature has already built into the fabric of reality. Think about that for a moment. The universe might already have a transportation network woven into its deepest levels. Quantum entanglement connects particles across arbitrary distances instantaneously. Wormholes, if they exist, could link distant regions of space-time. Dark energy is accelerating the expansion of the universe in ways we don't fully understand. All of these phenomena hint at connections and mechanisms that go beyond our everyday experience. We're like people living on the surface of an ocean, only now beginning to realize there's an entire world beneath the waves. And here's something that should absolutely blow your mind. The universe is around 13.8 billion years old. Our Sun is only about 4.6 billion years old. That means the universe existed for over 9 billion years before our solar system even formed. During that time, countless generations of stars were born, lived and died. Galaxies collided and merged, structure formed on the largest scales, and if life arose elsewhere, if other civilizations developed, some of them could be billions of years older than us. What could a civilization accomplish with a billion-year head start? What technologies might they develop? What understanding of physics might they achieve? If warp drives are possible, perhaps someone out there has already built them. Perhaps there are ships traversing the galaxy right now, moving faster than light, exploring worlds and cataloging wonders we can barely imagine. Perhaps we're the newcomers to a galaxy that's already been explored. That's pure speculation, of course. We have no evidence of alien civilizations, let alone alien warp drives, but it's worth considering because it puts our own efforts in perspective. We're not trying to do something that violates the laws of nature. We're trying to do something that nature might already permit, and if nature permits it, then it's at least possible that someone, somewhere, has figured it out. There's a concept in astrobiology called the Great Filter. The idea is that somewhere between the emergence of simple life and the development of advanced, galaxy-spanning civilizations, there's a barrier, a filter that most species don't pass through. Maybe it's the jump from single-celled to multicellular life. Maybe it's the development of intelligence. Maybe it's avoiding self-destruction through nuclear war or environmental collapse. Or maybe, just maybe, it's developing faster than light travel. If the Great Filter is ahead of us, if most civilizations fail to develop technologies like warp drives before they destroy themselves or stagnate, then our success or failure in this endeavor matters enormously. It determines whether humanity's future is measured in centuries or in eons, whether we remain confined to one fragile planet or spread across thousands of worlds, whether we're at a brief flicker in cosmic history or a lasting presence. But I'm optimistic. I think we have a real chance of making it through, because despite all our flaws, despite all the challenges we face, humans have one incredible quality. We're curious, we ask questions, we imagine possibilities, we build things, we solve problems, we don't give up easily. And those traits, that relentless curiosity and determination, have carried us from caves to cities, from Earth to the Moon, and might eventually carry us to the stars. Let's talk about some of the nearer-term steps we might take. Even if a full warp drive is decades or centuries away, there are intermediate technologies worth pursuing. For instance, we could develop drives that don't break the light speed barrier, but get us to significant fractions of light speed, 10%, 20%, maybe even 50% of light speed. At those velocities, interstellar travel becomes feasible, though still challenging. Several concepts exist for these sub-light speed drives: solar sails that catch the pressure of starlight, laser propulsion systems that beam energy to a spacecraft from powerful Earth-based or space-based lasers, fusion drives that use the same nuclear reactions that power the Sun, antimatter engines that annihilate matter, and antimatter for maximum energy release. None of these are faster than light, but all of them could dramatically reduce travel times within our solar system and make journeys to nearby stars possible within human lifetimes. And here's the beautiful thing: as we develop these technologies, as we push closer and closer to light speed, we'll learn more about how space-time behaves at relativistic velocities. We'll gain practical experience with the engineering challenges. We'll develop materials and techniques that might eventually prove useful for warp drive construction. Progress isn't linear, it's iterative. Each generation builds on the work of the previous one. The James Webb Space Telescope, which launched in December of 2021, is already revolutionizing our understanding of the universe. It's looking back in time to see the first galaxies that formed after the Big Bang. It's analyzing the atmospheres of exoplanets, searching for signs of life. It's revealing structures and phenomena we never knew existed. Every new discovery raises new questions, and some of those questions might eventually point toward new physics that makes warp drives more feasible. Similarly, missions like the Event Horizon Telescope, which captured the first image of a black hole in 2019, are probing the most extreme environments in the universe. Black holes warp space-time so severely that they create event horizons, surfaces beyond which nothing, not even light, can escape. Understanding how space-time behaves in these extreme conditions could provide insights relevant to warp drive research. Maybe there are lessons to be learned from nature's most powerful gravitational engines. And then there are the particle accelerators like the Large Hadron Collider at CERN, which smash protons together at nearly the speed of light to probe the fundamental structure of matter and energy. These machines have discovered new particles, like the Higgs boson, that help explain how the universe works. They might yet discover new physics, new particles, new fields that could be relevant to manipulating space-time. Every tool we build to explore the universe teaches us something new. There's a synergy between all these fields of research. Astronomy informs physics, physics informs engineering, engineering enables new observations. It's all connected, all part of the same grand endeavor to understand reality. And the pursuit of warp drives sits at the nexus of all these disciplines. It requires cutting-edge theoretical physics, innovative engineering, advanced materials science, and a deep understanding of how the universe works at every scale. Now let me address something that might be on your mind. Why should we care about this right now? Why pour resources into something as speculative as warp drive research when we have pressing problems here on Earth? Climate change, poverty, disease, political instability. Aren't there more important things to focus on? It's a fair question, and the answer is nuanced. First, it's not an either-or proposition. We're capable of working on multiple challenges simultaneously. The entire global space industry, including all government space agencies and private companies, accounts for less than $500 billion annually. That's significant, but it's a small fraction of global GDP, which exceeds $100 trillion. We have the resources to address earthly problems and pursue space exploration. It's a matter of priorities and allocation, not fundamental scarcity. Second, history shows that technological advancement often comes from pursuing ambitious, seemingly impractical goals. The Internet began as a military research project. GPS was developed for naval navigation. Countless medical technologies, from MRI machines to advanced prosthetics, have roots in space research. When you push the boundaries of what's possible, you inevitably discover things that have applications you never anticipated. The pursuit of knowledge for its own sake has always yielded practical benefits. Third, and perhaps most importantly, humanity needs a future worth working toward. We need hope. We need inspiration. We need to believe that tomorrow can be better than today, that our children and grandchildren will inherit a world of expanded possibilities, not diminished ones. The dream of exploring the stars provides that hope. It reminds us that we're part of something larger than our individual lives, our daily struggles, our petty conflicts. We're part of a species with the potential to become something truly extraordinary. That doesn't mean we should ignore our problems, it means we should solve them while simultaneously reaching for something greater. We should develop clean energy not just to reduce emissions, but also because we'll need advanced energy systems for space exploration. We should advance medicine not just to heal the sick, but also because we'll need robust health technologies for long-duration space missions. We should promote education not just to create informed citizens, but also because we'll need generations of brilliant scientists and engineers to tackle these challenges. Everything connects. Every problem we solve on Earth makes space exploration more feasible, and every technology we develop for space exploration helps us solve problems on Earth. It's a positive feedback loop, a virtuous cycle where progress in one area accelerates progress in others. And let me share with you a personal perspective. I find something deeply moving about the fact that we live in a time when these questions are transitioning from science fiction to science fact. For most of human history, faster-than-light travel was pure fantasy. It was the stuff of myths and legends, of gods and magic, not something serious people discussed. Even a century ago, when Einstein first proposed his theories of relativity, the idea of bending space-time for travel purposes would have seemed absurd. But now we have equations, we have models, we have researchers at respected institutions publishing papers on warp drive metrics and energy requirements. We have experiments testing the boundaries of what's possible. We have private companies and government agencies expressing serious interest. We're still in the early stages, absolutely, but we're further along than ever before. And that trajectory, that arc from impossible to implausible to maybe someday possible, is breathtaking. You, Josue, are living through a pivotal moment in human history. You're alive during the transition from a single planet species to a potential multi-planet and eventually multi-star civilization. The decisions made in your lifetime, the research conducted, the technologies developed, the values embraced will determine whether that potential is realized or squandered. That's both exciting and sobering. It's a tremendous responsibility, but also a tremendous opportunity. And you don't have to be a physicist or an engineer to contribute. The path to the stars requires people from every discipline, writers to tell the stories that inspire the next generation, artists to help us imagine what that future looks like, philosophers to grapple with the ethical dimensions, educators to ensure that knowledge is widely shared, policymakers to create frameworks that support exploration, entrepreneurs to find ways to make it economically viable. Everyone has a role to play. So what comes next? Where does warp drive research go from here? In the short term, we'll see continued refinement of the theoretical models. Physicists will keep searching for configurations that reduce the energy requirements further. They'll explore different geometries, different exotic matter distributions, different ways to couple quantum fields to space-time curvature. Every reduction in energy requirements brings us closer to feasibility. We'll also see more experimental work, tests of the Casimir effect at larger scales and in more complex geometries. Searches for exotic matter or negative energy density in extreme environments, studies of how quantum fields behave near black holes, neutron stars, and other high-energy phenomena. Laboratory experiments that probe the boundaries between quantum mechanics and general relativity. Each experiment, whether it succeeds or fails, teaches us something valuable. In the medium term, perhaps over the next few decades, we might see proof of concept demonstrations. Not full warp drives, but small-scale experiments that show we can manipulate space-time in controlled ways. Maybe we'll create micro-bubbles of warp geometry in a laboratory. Maybe we'll detect signatures of negative energy in carefully designed quantum systems. These would be huge milestones, confirmation that we're on the right track. And in the longer term, if we're lucky and clever and persistent, we might see actual prototypes. Small-scale warp drives that move objects short distances at faster than light speeds, then larger versions, then eventually spacecraft capable of carrying cargo, and ultimately people, across interstellar distances in reasonable time frames. This could happen in 50 years or 100 years or 500 years, we don't know. But the important thing is that it's no longer impossible, it's just very, very difficult. there's also the possibility of surprises. Science has a habit of taking unexpected turns. We might discover something completely unforeseen, some new principle or phenomenon that makes warp drives easier than we currently imagine. Or we might discover fundamental obstacles that force us to abandon the idea entirely and pursue different approaches to faster-than-light travel. Maybe quantum tunneling through higher dimensions. Maybe manipulating dark energy. Maybe something we haven't even thought of yet. The universe is under no obligation to make things easy for us, but it's also proven time and again that it's richer and more surprising than we expect. Every time we think we understand how things work, nature reveals another layer, another set of phenomena we didn't know existed. Dark matter, dark energy, quantum entanglement, gravitational waves. Each discovery opens new doors, raises new possibilities. And here's something wonderful to consider. Right now, somewhere on Earth, there might be a child who will grow up to solve the warp drive problem. Maybe they're in school right now, fascinated by science fiction, doodling spaceships in their notebook. Maybe they haven't even been born yet. But somewhere in the next generation or the one after that, there's a mind that will make the crucial breakthrough. They'll see the connection that everyone else missed. They'll ask the right question. They'll run the experiment that reveals the hidden mechanism. That person could be anywhere. They might grow up in São Paulo or Tokyo or Lagos or Mumbai. They might come from wealth or poverty. They might face obstacles and discrimination. But if we create a world where talent is nurtured, regardless of where it emerges, where education is accessible to everyone, where curiosity is encouraged and supported, then that person will have the chance to make their contribution. And when they do, we'll all benefit. This is why investments in education, in research infrastructure, in international cooperation, in creating open and inclusive scientific communities matter so much. We're not just solving today's problems, we're planting seeds for breakthroughs that might not come to fruition for generations. We're building the foundation that future scientists will stand on when they reach for the stars. Let me paint you a picture of what that future might look like. Imagine it's the year 2200. Humanity has developed functioning warp drive technology. It's expensive, yes. It requires massive infrastructure and careful planning, but it works. Several dozen ships have been built, each capable of traveling to nearby star systems in weeks or months rather than millennia. The first missions were scientific expeditions, robotic probes sent to catalog exoplanets, measure magnetic fields, study stellar atmospheres. Then came the crewed missions. Small teams of astronauts, scientists and engineers traveling to Proxima Centauri, to Tau Ceti, to Epsilon Eridani, setting up research stations, deploying telescopes and sensors, gathering data that could never be obtained from Earth. Then came the settlers, people willing to leave Earth behind and start new communities around distant stars. At first, just research outposts, but gradually growing into permanent settlements, small towns under alien skies. Children born who would never set foot on Earth, who would think of their new world as home, the beginning of humanity's true diaspora across the galaxy. By this point, hundreds of star systems have been explored, thousands of planets have been catalogued, and among them, inevitably, life has been discovered. Simple, single-celled organisms on some worlds, complex ecosystems on others. And then the discovery that changes everything, unambiguous signs of intelligent life. Cities, agriculture, technology, civilization, first contact, the moment when humanity learns definitively that we are not alone, that the universe is full of minds, full of perspectives, full of cultures and histories as rich and complex as our own. It would be the most significant moment in human history, a dividing line between everything that came before and everything that comes after. How would that contact unfold? What would we say to beings who evolved under completely different conditions. How would we find common ground? What could we learn from them? What could they learn from us? These questions are the stuff of speculation right now, but with warp drive technology, they become practical concerns, questions that diplomats and linguists and anthropologists would need to answer. And there's something beautiful about that possibility. The idea that our descendants might sit down with alien beings and share stories, compare notes on how the universe works, collaborate on solving problems that affect multiple civilizations. The idea that intelligence, wherever it emerges, might share certain common values. Curiosity. The desire to understand, the appreciation of beauty. The recognition that cooperation leads to better outcomes than conflict. Of course, it might not be that harmonious. Histology shows that when cultures with different levels of technology meet, the results are often tragic for the less advanced civilization. We'd need to approach any encounters with humility, with respect, with a commitment to doing no harm. We'd need to be the kind of civilization that we'd want to meet if we were the less advanced species. That's a tall order. It requires wisdom and maturity that humanity hasn't always demonstrated, but I believe we're capable of it. I believe we can learn from our mistakes. I believe that the same curiosity that drives us to explore can also drive us to ethical behavior. Because true exploration isn't about conquest or domination. It's about understanding. It's about expanding the circle of what we know and who we consider part of our community. Let me bring this back to the present, because I don't want you to think this is all distant future speculation with no relevance to your life. The technologies and principles we're discussing have applications right now. Understanding how to manipulate electromagnetic fields, how to work with exotic materials, how to model complex quantum systems. These skills are valuable in industries ranging from computing to medicine to manufacturing. The work being done on warp drive metrics informs our understanding of gravitational waves, which we're now detecting regularly thanks to facilities like LIGO and Virgo. Those gravitational wave detections help us understand black hole mergers, neutron-star collisions, and the fundamental nature of gravity itself. That knowledge has already led to refinements in GPS technology, improvements in timekeeping, and better models of how the universe evolved. Similarly, research into quantum field theory and the Casimir effect is driving advances in nanotechnology. When you can understand and control forces at the quantum level, you can design materials with properties that don't exist in nature. Super strong materials, perfect insulators, ultra-efficient conductors. These materials have applications in everything from electronics to transportation to construction. The point is, even if we never build a functioning warp drive, the pursuit of that goal is already paying dividends. It's pushing us to ask deeper questions, develop better tools, and expand our understanding of how reality works. And that understanding has value in itself, independent of any specific application. There's also a cultural dimension worth considering. Science fiction has always been a laboratory for ideas about the future. Stories about warp drives, about starships and alien encounters, about the challenges and wonders of exploring the cosmos, shape how we think about what's possible. They inspire people to pursue careers in science and engineering. They make the future feel tangible, something worth working toward, rather than something to fear. When people watched Star Trek in the 1960s, they saw a vision of the future where humanity had solved its problems and turned its attention outward to the stars, where diversity was celebrated, where science and reason guided decision-making, where exploration was valued for its own sake. That vision influenced generations of scientists, engineers, and leaders. It provided a blueprint for the kind of civilization we could become. Today's science fiction serves the same role. Stories about warp drives, about the challenges of interstellar travel, about encountering alien life, they're not just entertainment. They're thought experiments. They're ways of exploring possibilities and working through implications before we have to face them in reality. They help us think about who we want to be when we finally reach the stars. And increasingly, that science fiction is being written with real science in mind. Authors consult with physicists to make their warp drives plausible. They incorporate actual research into their stories. They grapple with the real challenges, the energy requirements, the exotic matter problems, the time dilation effects. This creates a virtuous cycle where science informs fiction and fiction inspires science. I want to circle back to something I mentioned earlier, the profound philosophical implications of faster-than-light travel. Einstein's theory of relativity doesn't just tell us that nothing can exceed the speed of light. It tells us that space and time are interwoven into a single fabric, space-time, and that the passage of time depends on your motion through space. This leads to effects like time dilation, where astronauts traveling at high speeds age more slowly than people who remain stationary. If we could travel faster than light using a warp drive, we'd sidestep many of these relativistic effects. The crew inside the warp bubble would experience normal time. They wouldn't age more slowly or experience the strange time distortions that occur at near-light speeds. From their perspective, they'd simply travel from point A to point B in a reasonable amount of time. This makes interstellar travel practical in a way that conventional relativistic travel never could be. But there's a deeper implication. Relativity tells us that the sequence of events, what happens before and what happens after, can depend on your frame of reference. For objects moving slower than light, this doesn't cause paradoxes. But with faster-than-light travel, you could potentially create situations where causality appears to be violated, where effects precede their causes, where you could, in principle, travel back in your own timeline. This is one of the reasons physicists are so cautious about faster-than-light travel. It's not just an engineering challenge. It potentially opens the door to time travel paradoxes. What happens if you travel back in time and prevent your own departure? What happens to causality, to the logical structure of reality, if effects can precede their causes? Now, there are several possible resolutions to these paradoxes. One is that the universe simply doesn't allow configurations that lead to paradoxes. Maybe there are hidden constraints, principles we haven't discovered yet, that prevent you from using warp drives to create closed time-like curves. Maybe space-time itself resists arrangements that would violate causality. Another possibility is the many-worlds interpretation of quantum mechanics. In this view, every time you make a choice or a quantum event occurs, the universe branches into multiple versions. If you travel back in time, you're not traveling back in your own timeline. You're traveling to a parallel universe that diverges from yours at that point. You can't create paradoxes because you're never actually changing your own past. A third possibility is that causality is more flexible than we think. Maybe the universe can accommodate closed loops in time without breaking. Maybe what seems like a paradox to us is actually perfectly consistent when viewed from a higher dimensional perspective. Maybe time isn't the simple linear sequence we experience it as, but something far more complex and interconnected. We don't know which, if any, of these interpretations is correct, but the fact that warp drives force us to grapple with these questions is valuable in itself. It pushes us to think more deeply about the nature of time, causality, and the structure of reality, and those are questions worth asking, regardless of whether we ever build a functioning warp drive. There's also something called the chronology protection conjecture, proposed by Stephen Hawking. It suggests that the laws of physics might conspire to prevent time travel, even if faster-than-light travel is possible. Maybe quantum effects cause warp bubbles to collapse before they can be used to create closed time-like curves. Maybe exotic matter becomes unstable in configurations that would allow time travel. The universe might have built-in safeguards against paradoxes. This is still an open question in physics. We don't have a complete theory of quantum gravity that would let us definitively answer it. But the fact that we can ask the question, that we can model these scenarios mathematically and explore their implications, shows how far we've come. We're probing the deepest foundations of reality, asking questions that would have seemed like pure philosophy a century ago, but are now legitimate topics of scientific inquiry. Let me share one more exciting development with you. In recent years, there's been growing interest in analog models of space-time. These are laboratory systems, things like flowing fluids or metamaterials, that mimic some properties of curved space-time. They don't actually warp space-time in the way a real warp drive would, but they create mathematical analogies that let us study similar effects in controlled settings. For example, flowing water can create an acoustic event horizon, a point where the flow speed exceeds the speed of sound waves in the water. Sound waves can't escape from beyond this point, just like light can't escape from beyond the event horizon of a black hole. By studying these acoustic black holes, we can learn about phenomena like Hawking radiation without needing an actual black hole. Similarly, researchers have created optical systems where light behaves as if it's moving through curved space-time. These systems let us test predictions about how light would propagate in exotic geometries, including some of the geometries proposed for warp drives. They're not perfect analogues, but they're incredibly valuable tools for building intuition and testing ideas before we can create the real thing. This approach, using analog models to study phenomena we can't yet create directly, has a long history in physics. Before we could create quark-gluon plasmas in particle accelerators, physicists studied analogous systems in condensed matter physics. Before we could observe gravitational waves, we studied similar wave phenomena in other contexts. Analogues help bridge the gap between theory and experiment. For warp drives, analog models might let us test how matter and energy behave in regions of strong space-time curvature. They might reveal instabilities or unexpected effects that aren't obvious from the equations alone. They might help us understand what kinds of exotic matter distributions are actually realizable, not just mathematically possible. Every insight we gain from these models brings us closer to knowing whether warp drives are truly feasible. And there's another benefit to this work. Even if warp drives turn out to be impossible, the techniques we develop for manipulating electromagnetic fields, for creating exotic material properties, for controlling quantum systems, all of these have other applications. We might discover new types of cloaking devices, new methods for concentrating or redirecting energy, new ways to shield sensitive equipment from interference. The pursuit of one goal often leads to unexpected breakthroughs in other areas. This is the beauty of scientific research. It's not a straight line from question to answer. It's a web of interconnected investigations where progress in one area enables progress in others, where dead ends teach us valuable lessons, where unexpected discoveries open entirely new fields of inquiry. The pursuit of warp drive technology fits perfectly into this pattern. Now I want to address something important. Throughout this conversation, I've tried to balance optimism with realism. I've emphasized the possibilities while acknowledging the enormous challenges, and I think that balance is crucial. We need to dream big, to reach for seemingly impossible goals, because that's how humanity has always made progress. But we also need to be honest about the obstacles, the uncertainties, the very real possibility that some things might not work out the way we hope. Warp drives might never be built. The energy requirements might prove insurmountable. Exotic matter might not exist in the forms we need. There might be fundamental laws of physics that prohibit faster-than-light travel, safeguards we haven't discovered yet that prevent causality violations. We might pursue this goal for centuries and ultimately conclude that it's not possible. And if that happens, it won't be a failure, it will be knowledge. We'll have learned something profound about the universe. We'll have developed technologies and techniques along the way that have other applications. We'll have inspired generations of scientists and engineers. We'll have pushed the boundaries of human understanding. And we'll turn our attention to other approaches, other possibilities for exploring the cosmos. Maybe we'll perfect generation ships, massive vessels that travel for centuries or millennia at sub-light speeds, carrying entire communities across the stars. Maybe we'll discover ways to extend human lifespan indefinitely so that individual people can survive the long journey. Maybe we'll develop techniques for suspended animation or digital consciousness transfer. Maybe we'll find shortcuts through higher dimensions or exploit quantum entanglement for instantaneous communication and eventually transportation. The universe is vast and complex. There are many paths forward, many possibilities we haven't fully explored. Warp drives represent one promising avenue, but they're not the only one. What matters is that we keep pushing, keep exploring, keep asking questions and seeking answers. That's the essence of what it means to be human. We're a curious species. We look at the horizon and wonder what's beyond it. We look at the stars and dream of reaching them. And here's something that fills me with hope. Every generation faces challenges that seem insurmountable. Every generation inherits problems from the past and creates new ones for the future. But every generation also makes progress. We solve problems that our ancestors couldn't. We achieve things that were once thought impossible. We expand the realm of what's known and what's possible. Your generation, Josue, and the generations that follow will face enormous challenges: climate change, resource depletion, political instability. The ethical implications of artificial intelligence and genetic engineering, the risk of existential threats from technology or natural disasters. These are real problems that demand serious attention and innovative solutions. But you'll also have tools and knowledge that previous generations couldn't imagine. You'll have computational power that lets you model complex systems with incredible precision. You'll have materials and manufacturing techniques that enable structures and devices we can barely conceive of today. You'll have a global communication network that connects brilliant minds across the planet. You'll have the accumulated wisdom of all of human history at your fingertips. And most importantly, you'll have the same drive, the same curiosity, the same determination to overcome obstacles that has characterized every successful generation throughout history. You'll look at problems that seem impossible and find ways to solve them. You'll stand on the shoulders of giants and reach even higher. You'll turn today's science fiction into tomorrow's reality. The warp drive is a perfect symbol of that potential. It represents the audacious belief that the universe is knowable, that its mysteries can be unraveled, that its boundaries can be crossed. It represents the conviction that humanity's story doesn't end on Earth, that we're destined for something grander, something that spans the stars. Whether or not we ever build a functioning warp drive, that belief matters. It shapes how we think about ourselves and our place in the cosmos. It gives us something to strive for, a North Star to guide our efforts. It reminds us that we're part of something larger than ourselves, part of a species with the potential to become truly extraordinary. So where does this leave us? What's the takeaway from this long exploration of warp drives, exotic matter, space-time manipulation, and the future of human civilization? I think it's this: the universe is far stranger and more wonderful than we ever imagined. The boundaries of what's possible keep expanding, and we're living in a time when questions that were once pure fantasy are becoming legitimate scientific inquiries. The warp drive might be built in 50 years or 500 years or never. But the fact that we can seriously discuss it, that we have equations and models and experimental proposals, that represents progress. It represents humanity's relentless drive to understand and explore. And you, Josue, you're part of that story. You're living through a pivotal moment in human history. The decisions made in your lifetime will shape whether humanity becomes a multiplanetary, multistellar species, or whether we remain confined to Earth. the technologies developed, the values embraced, the priorities chosen, all of these will determine our trajectory. That's both exciting and humbling. It's a tremendous responsibility, but also a tremendous opportunity. You have the chance to contribute to something that will echo across generations, across centuries, potentially across the galaxy. So stay curious, keep asking questions, keep learning, support science and education and exploration. Dream big, but do the hard work to turn those dreams into reality. And remember that every breakthrough, every discovery, every moment of understanding brings us one step closer to the stars. The journey to develop warp drives, to explore distant worlds, to encounter alien civilizations, to become a truly spacefaring species, that journey begins with conversations like this one. It begins with people like you, Josue, wondering what's possible and committing to finding out. The universe is waiting, the stars are calling, and humanity is just beginning to answer. But what if we can't crack faster than light travel? What's the alternative? That's where generation ships come in. Massive vessels designed to carry humanity across the stars over centuries. Click on the video on your screen right now to discover the dark truth about generation ships.